All right, so we're on to section 7.3 today, and this one is, I know I say this a lot, but this is one of my favorite applications of integration. It is super cool. So in order to be able to do this, you should probably know how to find these different areas. Really what we rely on heavily is the area of a circle, but these shapes do show up as well. So just knowing how to find these areas in terms of a single variable, maybe pause the video, come back, and now you can see right here. So if you have any questions on how to set up these formulae, you might want to ask in class or come to office hours for that one. The ones that I see, like I said, we usually use circles a lot, but I have seen squares pop up on the AP test before, as well as maybe once or twice an equilateral triangle. But yeah, all right. So looking forward here, that would have been the homework, but we don't have that right now. So here we have finding the volume of a pyramid. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. Find the volume of the pyramid. So we have two options for this. One is the lame old school way of using geometry for this one. And the second option is using calculus and making it really cool on how to do this. Just as a side note, as I've always told you guys, no matter how you do a problem, as long as you do it correctly, you should get the same answer, because in math, there really is only one answer. So if we wanted to look at what the volume was doing the lame way using geometry, we know that the volume for a pyramid is 1/3 the area of the base times the height. So in this case, we have the base as a square, which is 3 meters. So 3 meters squared to get the base times the height, which is, in this case, 3 meters. So we have 1/3 of 3 squared times 3 meters, which would be giving us, I believe, 1/3 of 27, so 9 cubic meters, right? So we know the volume is 9 cubic meters, and that is the, I'll call it the lame way of doing it. The cooler way to do this is, again, using calculus. So let me show you how to do that. So first off, you can see that I've taken my pyramid from right here, the three-dimensional shape, and I've laid it on its side. The reason why I've laid it on its side is so that I can align the size of the size of one side length with the height of the pyramid. So looking in here, you can actually see that we could move this square to wherever we want, and we could determine the width of the square or the base of the square by how far from the tip of the pyramid it is, from the vertex, I guess I should say. So looking at that, if I was to graph that on the XY axis, I know that I start where the corresponding square has no width. That's right at the vertex of the pyramid. And then we have this right up here, which is 3 meters width at 3 meters height of the pyramid. So I can connect those two just to see that the height of the pyramid is going to be equal to the width of the pyramid at any given point. So we have y is equal to x in that case. So we do want to keep in mind that that allows us to see the width of the pyramid based on the height again. Now looking here, the next thing that we want to do is draw in what we call a typical cross-section of the pyramid. And the typical cross-section of that pyramid, again, is going to be a square. So when I'm drawing this square, I'm trying to draw it coming out from the paper, so you can see that I put a little bit of an angle on it to really see, okay, so I'm not a great artist, but we can kind of see that that cross-section is coming out. You might be able to see it a little bit better over here, where we have lining up with the line y equals x and coming out from the paper. Now what I like to do here is I like to take that typical cross-section and I like to just draw it in the foreground. And what I'm going to do here, I'm going to find the area of the typical cross-section. So the area in this case, it's going to be a square. and I know that my square is going to be the side length squared. Now the side length here is actually equal to whatever the y value is in this function. So the y value is actually equal to x. So the area of this square is going to be x squared. Now instead of thinking of this as a square, I'm actually going to want to think of it as kind of a rectangular prism like that. So it's more like a layer there. And what we're going to do, we're going to take multiple layers and we're going to add them together. So I'm going to add all of these square prisms on top of each other, and keep in mind they're going to be different widths here, and when I add them all together it's going to resemble a pyramid. Now I don't have one of these pyramids available to me right now, but if you Google ziggurat, you can actually see what this looks like. It's the Mayan Aztec pyramids that exist in Central America, or you can actually look, I have something similar to it. This is called the Tower of Hanoi. It's a puzzle, but this puzzle has these little discs, and these discs, when you separate them, they just look like circles with a little bit of a thickness to them. But when you add them all together, they resemble a cone. So we're going to have the same kind of thing when we're talking about building this pyramid, but we're going to add all these squares on top of each other. There we go. So when we add all those squares on top of each other, we can actually use the volume of these squares to produce the volume of the pyramid. So our volume of our cross section here is going to be the x squared times the thickness of our square. Now the thickness of our square here is kind of like this little change we have right here. So see how that little square prism is getting added on there? So our volume is going to be delta x. If we want to add all of those volumes together, that's a volume of just one cross section, but our total volume, big V here, is going to be the sum of all of the areas of those little tiny squares. Now we know in order to make this as good as possible, we want those squares to have very negligible width. So we want to make sure that they have almost a zero width to them. So delta x is going to be infinitesimal. And we know when we jump to that infinitesimal, instead of talking about a sigma, we talk about an integration symbol. Integral of x squared, and the delta becomes a dx. So that's how we're going to find our volume. Now here we do have to acknowledge that we have to use our limits. We're starting at the 0 square, and we're moving up to the 3 square. So it's going to be the integral from 0 to 3. Now we can actually get, using the fundamental theorem of calculus, the antiderivative of x squared, which is 1/3 x cubed, running from 0 to 3. So we can get 1/3 times 3 cubed minus 1/3 times 0 cubed. And 1/3 of 3 cubed is 1/3 of 27, which is 9 cubic meters is the volume of the pyramid. Now again, you could do it in this dumb geometry way if we were still in geometry, but now we're in calculus. We want to do it the cool way. Now to run through those steps that I like to use for this, I like to use the steps, okay, there we go. These 4 steps. Now full disclosure on these steps, I did steal this from somebody else, so I don't do it exactly this way. So step 1 is you sketch the solid and a typical cross section. I do that. The second step is find a formula for v of x. What I actually like to do is find a formula for a of x, and then just acknowledge that the volume of that cross section is going to be a of x times dx. So really, instead of finding v of x, I find a of x. And in the next step, I just multiply it by dx. But either way, it's going to be the exact same thing. Find the limits of integration. Sometimes they're going to be given to you. Sometimes you have to find them by finding intersections of different features in the plane, in the Cartesian plane, sorry. And then integrate v of x to find the volume. All right? The way book does it, is the definition of a solid of known integrable cross-section area A of x. From x equals a to x equals b is the integral of a from a to b, where the volume is equal to the integral from a to b of a of x dx. So I kind of lean on those 4 steps on the previous page and kind of lean on this formula, kind of a hybrid there. All right, so here is our first really freaking cool problem. So we have the region between the graph of f of x is equal to 2 plus x cosine of x, and the x-axis over the interval from -2 to 2 is revolved around the x-axis to make a solid. Find the volume of said solid. So the first thing that you have to do in this type of problem, you have to figure out what the function looks like. And the way that I would prefer to find out what the function looks like, especially considering we have a trig function multiplied by an x and then adding 2 to it, I would lean heavily on some sort of grapher, some sort of like your Texas Instruments grapher, or, oh, I know what I have. I have this graphed on GeoGebra. And you can see this link right down here, this URL. This is where I'm going to experiment with this really cool thing that I'm about to show you. I have also put that link in the Schoology folder, so if you want to play around with this cool tool, feel free to follow that link. Now here is what it looks like. That is the graph of the function. So the first thing that I'm going to do, and please note that the graph of the function is from -2 to 2. I limited my domain on my grapher just to make sure that I only show from -2 to 2. So I'm going to sketch that on my graph. All right, so, oh, where'd I put my pen? There we go. So we know going from -2 to 2, this function is going to look roughly like, and I already forgot what it looks like. Okay, so just sketching that. Looks like I got it pretty right? Doesn't have to be 100% accurate. We're not super artists here. Yeah, I got it pretty good. Not dead on, but pretty darn accurate. So now what we're going to do, we know that the problem says we revolve the function around the x-axis to make a solid. Now looking here, it kind of looks like I have this function graphed twice, doesn't it? But the difference between this graph and this graph, in case you can't tell, is over here on this graph, I can actually, I thought I could. Oh, there it goes. Whew, man, I had some lag going on that graph right there. So I have, looking at it dead on, but this is also a 3D graph, so you can actually see it from all angles here. And what I'm going to do, I'm going to take this function and I'm going to rotate it. The x-axis is the red axis right here. So I'm going to rotate it around the red axis. And the way that I can do that, I actually have this slider tool right here. And see, I can just take that. Okay, so I've got some severe lag on this. I apologize for that. So you can see I can rotate that around the x-axis. And what I have going on here, I have something called a trace going on that function. So as I'm rotating this function around, see it's kind of cementing some of those versions of the graph as I rotate it around. I'm going to pause this and try to get some more going on that. All right, so here we go. I've added quite a few more in there, and you can see that this three-dimensional rendering right here looks more like a vase, or sometimes people have called it a doorknob, where you got the graspy part over here, and here's the part that attaches to the door. Whatever you're looking at, you get a feel for what this function looks like when you rotate it around the x-axis. And as we rotate it around the x-axis, notice that each point is following this cross-section right here. And that cross-section, as long as I rotate around that axis, is going to be one singular shape. And that one singular shape is going to be a circle. So if we're looking at how to rotate about an axis, we know that if we rotate about an axis, the cross section will always be circular. And again, we're taking all of those circles and we're adding them together. I think actually I can grab that point and move it around here. Thought I could. Oh wait, maybe I have to grab it over here. You can see as soon as I move stuff around, all of a sudden my traces go away. But as I go up and down here, those circles have different radii, they have different area. So we can see that the area of our cross section is dependent on how far through this experiment we've gone. So back to the way that I like to illustrate that rotation around the x-axis. Maybe I can put up my picture right up here. So I'm again seeing that this is rotating up and back. So when I rotate up and back, I know that this is going to be reflected over the x-axis to give me the silhouette of my shape right there. And then once I get the silhouette of my shape, I start trying to draw in my cross sections. Now keep in mind, I am not an artist, so when I draw them, I kind of have a little bit of coming up and a little bit of going back. The going back I put as the dashed kind of drawing there. And I just throw in a couple of cross sections so that I can get the feeling for what the actual figure looks like. There's no right or wrong for how many cross sections you put in here, just enough for you to get the feeling of what it looks like. So that gives me a feeling of that vase kind of looking thing. I always refer to this as a spittoon, where you used to have in the Old West where people would spit their chewing tobacco. Maybe that's not exactly appropriate, but whatever. All we have to do is get an idea of what this solid looks like. Now we take that solid, we take a typical cross-section of that solid. The typical cross-section of that solid, again, is a circle. So I've just taken this circle that's coming off my paper right over here, and I've physically picked it up and went like that. All right, so I'm gonna draw some features in here. I'm gonna draw the center of the circle, and I know that a common feature in my circle is a radius of my circle. So I draw my radius going up like this, and I can see that I have a radius like that. So now I'm going to try to find the area of my typical cross section. To find the area of my typical cross section, again, I know that my cross section is a circle. So I know that I'm going to have pi r squared. My pi r squared, okay, so now I need to find out what my radius is. My radius here is my height. So my radius is going to be my y. Oops. Now I know ultimately, since I'm doing my cross sections, what we call vertical cross sections, we'll get into horizontal cross sections in a minute. I know that I need to have this in terms of x, because again, my little slidey along parts for my cross sections are going to be that delta x. Now it's going to be into the dx, so I need to put this in terms of x. If only I knew what y was in terms of x. Oh, I do. I've got pi times, oops. I forgot the 2. Oh my gosh. Pi times 2 plus x cosine of x squared. Now I know in order to find my volume, I'm going to take all of these disks, I'm going to add them together, so I know that I am talking about the integral. Integral of the area times the height of each what do we call these? Let's call them something that's a circular shape, disks. Let's just call them disks. So we're going to have pi times our 2 plus x cosine of x squared dx. We need to find our limits. Our limits are given to us, going from -2 up to 2, and now we need to integrate that. Now, before we get into actually integrating this, I am going to say we're going to cheat on this one and just use our calculator. Notice that we have a square of a function, so we have a composition of a function. If we tried to use U substitution. The U just wouldn't be there, so it's going to be really bad if we try to do this by hand. So I am just grabbing my calculator, getting to my home screen. I said getting to my home screen, and then just typing in exactly what's on my screen right now. The alpha window 4 integral from -2 to 2 of pi times 2 plus x cosine x. Watch my parentheses here so that I get all that 2 plus x cosine x squared and dx. We get a total volume of 52.429 cubic units here. Now let's say I wanted to ensure that I don't screw up on my parentheses, which is a big concern there. I could have, when I graph this, I know that I had to graph 2 plus x cosine of x. I could put that into the y equals menu, and when I go to my home screen, when I do the -2 to 2, I can just put in pi and use my vars menu and square that. That way I don't have to worry about those parentheses. Notice I do get the same answer either way. I do just think that the second way of doing that is going to be a little bit easier to not make mistakes. So again, we have is approximately 52.429 cubic units. So I don't think we were given any units here. Yeah, so cubic units here. All right. Now this is a common setup for problems. This is called the disk method for finding the volume of a solid. Before I give you the actual formula for the disk method, let's just do another one. We've got y equals square root of x. So I start with this curve, y equals square root of x. My boss at the Acme Rocket Company has assigned me to build a nose cone in this shape. So we can see nose cone drawn right here. I put a piece of wood in a lathe and turn it to a shape to match the curve. So if you've never seen what a lathe is, just go on YouTube and look at a video. It actually really illustrates this whole rotating around an axis. Another thing that you can think of for rotating around an axis is throwing clay on a potter's wheel is something that some other people have thought of in the past. But anyway, we look at it, we know we're taking this curve, we are moving it up and around the axis, so we're going to have that reflection to get the silhouette of the shape, and we're going to throw in some of our cross sections. So again, how many cross sections do you need to show this shape? I don't know until you can see it take form. Or even not. I mean, you could probably do this without actually knowing what the shape of the what the shape looks like. I just find that makes it a little bit easier to work with, because now I can easily see what my cross section is. And my cross section is, again, going to be that circle. I'm going to draw my axis right in there. Again, keep in mind that this is if you were able to take this shape and just like turn it so that you're looking dead onto it. Just like I did in that 3D grapher that we had. So looking back here, again, I can see that my radius goes up. So I like to draw that in there just so that I can get what the area of the cross section is going to look like. Now I can say that my area is going to be that pi r squared. Again, my r in this case is going to be my y. So I'm going to have pi y squared, but again, I know that I'm moving these disks along the x-axis, so I know that the thickness of the disks is going to be delta x, which translates into dx, so I need to put this back in terms of x, so this is going to be pi times the y is equal to, oh, hey, look at that, it's square root of x, so pi times square root of x squared. So now I can figure out that my volume of my nose cone is going to be the integral of the area times the thickness. So So the area would be pi. Oh, I don't like this redundancy. You guys know that I hate redundancy. Square root squared. That's just going to be pi x dx. Now I do have to acknowledge what my limits are here. I think just reading into this situation, we can see the graph is clearly showing us that we want a nose cone that is 4 units high. We don't know the units, so again, we're going to have to put it at units. So we would go from the nose cone, the circle, the 0 circle, up to the 4 circle, and add all the ones in between there by just using some calculus. Now looking at this, I see it's a really easy integration to do, so I'm going to do it by hand. On this upcoming test, there is nothing that you have to do by hand as far as the integration is concerned, so you can dump this into a calculator if you want to. But why would I want to when I see that pi is just constant multiple? I slide it out there, and then realize I'm just doing the integral of x dx. So this becomes 1/2 of x squared, running from 0 to 4. I know using the fundamental theorem of calculus, I'm going to have pi times the quantity of 1/2 of 4 squared minus 1/2 of 0 squared. Half of 4 squared is half of 16. 8 minus 0, forgot my parentheses there. 8 minus 0 gives me 8 pi cubic units. Again, it's up to you how you want to do it. I feel cooler when I do it by hand. You might feel cooler by doing it using your calculator. I don't care how you do it, although if you are taking the AP test, probably be a good idea to do some practice doing it by hand. Oh, and by the way, I would accept whatever the answer of 8 times pi is, as long as you round to 3 decimals. So again, I think I jumped the gun a little bit on telling you guys what this was called. It is called the disk method. This application of the method of slicing is called the disk method. The shape of the slice is a disk, so we use the formula for the area of a circle to find the volume of a disk. If the shape is rotated about the x-axis, then the formula is integral from a to b of y squared dx. Since we will be using the sorry, I stole this from somebody else, and this part does not apply to you guys because we do not have formula quizzes in this course. Apparently some other calculus teacher did like to use formula quizzes. Now, down here at the bottom, a shape rotated about the y-axis would be v is equal to pi times the integral from a to b of x squared dy. So a note there is if we change the directions and say rotate about the y-axis, we put everything in terms of x. And why would we want to do that? Because we'd be asked about it. So when we talked about the area in the plane from last section, we really had to analyze whether we used it in terms of y or x. Here, you are going to be told whether it's in terms of y or x. Like in this problem, the region between the curve x equals 1 over the square root of y between 1 less than or equal to y less than or equal to 4, and the y-axis is revolved about the y-axis. So find the volume. So you can see I've actually drawn the curve 1 over the square root of y right here. If you don't know what that curve looks like, you could use some external grapher tools like Desmos or GeoGebra to get the idea there. But we've actually drawn in the cross sections here. We know since we're rotating about an axis, 100% guarantee when you rotate about an axis, you're going to be using some sort of circular cross section. Looking at that solid, I would call that like a lampshade. That's just where my mind goes to it. If you like the band Devo hat, if you will. But any way you look at it, we have our cross section is a circle. Now notice that radius is drawn in here for us. I draw my radius like this. And acknowledging that since my discs are sliding up and down, the thickness of that disc is going to be the delta y, and when we make that negligibly thick, it's going to become dy. Why do I do that? So that I recognize when I have the area, I'm going to have my pi r squared, but in this case, my r is going to be x squared, which would be pi, since I'm getting it down to the dy, I know that this is going to have to be in terms of y. This would be pi times 1 over the square root of y squared. And let's remove our redundancy right now so that we can get this to be pi times 1 over y. So that now we know that the volume is equal to the integral of pi times 1 over y dy. And if we go back to that previous page on this flip chart, whoever I stole this formula from automatically put the pi out in front. You can do that if you want to, but I like to do the same setup for every single problem to make it, it makes it easier in my mind. Now we look at this, we want it to go from 1 to 4. And now all we have left is integrate it. You want to grab your calculator, go ahead and grab your calculator. But I happen to see 1 over y, which to me, I've really drilled this one home into you guys, ln of y would be my integral there, from 1 to 4. I know that this would become pi times the quantity of ln of 4 minus ln of 1. I know ln of 1 is 0, so this becomes pi times ln of 4. So to me, that's a little bit easier than typing it into my calculator. Of course, I would accept, if you used your calculator, whatever the decimal approximation is off of this. Again, as long as you round to 3 decimal places. So you can see we actually have like really one type of problem so far. It's all find the cross section, find the area of that cross section, and integrate that cross section. Here's another common problem that comes up. We have a region bounded by 2 functions rotated around the around an axis, and when we rotate an area bounded by 2 functions around an axis, we actually end up with some sort of 3-dimensional figure with a hole in the center of it. On this one. Now this one in the past has been difficult for people to envision. What I think of is like it's like that nose cone that we did previously, but there's a cone drilled out on the inside of it. So it could be some sort of tank for holding water. It could be a cereal bowl if you're thinking about that one. It could also be a headlight for a motorcycle where you can keep the components inside of there, like the light bulb and the reflectors and all that stuff inside of the housing for the headlight. A bunch of different things, but you have to recognize that it's a 3-dimensional figure. Now you can see we've actually drawn that y equals x squared, we've drawn the y equals 2x, and we've actually reflected those over the y-axis because again we're rotating around the y-axis because the directions tell us to do that here. Sorry, that's what I was trying to do. I was trying to get this back up here. If we need to draw more cross sections in here, note that we can have another cross section right here where I'm going to have to draw both circles in there. So it's like a circle with a circle removed in here. They're actually giving you a term for it. It's a common term that we use for it. It's called a washer, which lends the name to this method called the washer method. Why it's called the washer method is because we have a cross section that looks like this. In the past, I've had some people call that the donut method. I don't care what you call it. When you talk to people about calculus, they'll probably call it the washer method just because that's so common. But anyway, you look at it, we have our y-axis is the center of a rotation, so it's going to be the center of our circle. And then noticing that our radii here are going off to the side to meet up with the circle. So looking at that, we can have there is our, actually we won't say radius this time, we will talk about radii since we have 2 circles. And we know in order to find the area of this circle, or sorry, not this circle, we want to find the area of the space in between the circles here. Because we don't want to count all that area in the middle. That's being drilled out of this 3-dimensional figure. So our area is going to be the area of the big minus the area of the small. Now when we talk about big and small, we can talk about our big radius and our little radius. The way that we refer to those are going to be big R and little r. Alright, so this area is going to be, oopsies, forgot what my area formula for a circle was. Oops, pi times big R squared minus pi times little r squared. So here's where I don't really keep reproducing this every single time. I like to jump right to this step where I can factor out the pi. This area of that washer space is just going to be pi times the quantity of big R squared minus little r squared. And to find that big R and that little r, we need to keep in mind, since we're talking about our thickness being dy here, we want everything to be in terms of y. So it's going to be the outer function, which looking here, the outer function is the quadratic. When we put it in terms of y, it's going to be square root of y. So this would be equal to pi times the quantity of square root of y squared minus the inner function, which was 2x, the linear one. We solve it for x, and we get it in terms of y. It would be minus y over 2 squared. Removing redundancy and getting it to look, somewhat manageable, this would be pi, root y squared would give me y minus y squared over 4. So there's the area of my cross section. Again, if I was doing this in the wild, I would probably jump from here right over to here, or maybe even to here. I don't know. I don't 100% of the time put out big R and little r. It might be helpful just to put that down every time, but I honestly don't do that all the time. So our volume, again, we've got the area of our cross section is going to be the integral of pi times the quantity of y minus 1y squared over 4 dy. Now here we're not given our limits, so we do have to find our limits. To find our limits, we do have to set the two equations equal to each other, so it's up to you whether you want to say y equals x squared equals 2y or square root of y equals y over 2. I think that solving it as x squared is equal to 2x is the easier option, because then I can get x squared minus 2x is equal to 0. I got x times the quantity of x minus 2 is equal to 0. Leads me right into x is equal to 0. And x is equal to 2, but I do recognize, since I'm doing my horizontal slices here, I'm going from the y equals 0 up to this y value up here. I do need to acknowledge what my y coordinates are here, so I've got 0, comma something, and 2, comma something else. To find that something else, choose whichever equation is easier to plug into. Whether I do 0 squared or 2 times 0, I'm going to get 0 over here. And whether I do 2 squared or 2 times 2, I'm going to get 4 up here. All of that is just to say that our limits are from 0 to 4. Since everything is in terms of y, we want to use the y's as our limits. Now again, as I've been saying every single time here, it's it's fine if you want to grab your calculator here. I wouldn't, but I'm not you. I would put this as 1/2 y squared minus 1/12 y cubed, running from 0 to 4. So I can see that I have pi times the quantity of 1/2 4 squared minus 1/12 4 cubed minus 1/2 0 squared minus 1/12 0 cubed. All zeros over there, so I cross them out. I'm really left with pi times the quantity of half of 4 squared, so pi times 8 minus 1/12 of 4 cubed. 4 cubed is 64, so I have 1/12 of 64. Okay, maybe I should grab my calculator. I'm not going to. I know that's going to become 3 and 16. So 8 minus 16 thirds is going to become pi times quantity of 24 thirds minus 16 thirds. Man, this is fun. 8 thirds of pi. So 8 thirds of pi cubic units is going to be the volume of my whatever you want to call it, headlight, bowl, water tower, whatever. 8/3 pi. Yeah. Arithmetic's sometimes fun. So again, here we have, this is called the washer method. We take the disk, we drill out the inside, and it looks like a washer. So this application of the method of slicing is called the washer method. The shape of the slice is a circle with a hole in it, so we subtract the area of the inner circle from the area of the outer circle, and the washer method formula is v equals pi times the integral from a to b of r squared minus r squared dx, or dy, depending on what axis you're rotating this around. I will point out that there is another method that you could use to find volumes like this. It is called the shell method. I'm not going to teach the shell method because every single problem that is on the AP test, we are told that you can solve using the washer method. So if you want to go out and look for the shell method, it's fun, but you don't have to do it. Looking a little bit further, ooh man. A solid is made so that its base is the shape of the region between the x-axis and one arch of the curve, y equals 2 sine of x. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. So this is a little bit different from the other problems that we've been talking about. This is a non-circular cross-section. Those do pop up just like that first example with the pyramid. Again, I'm not too good of an artist, so I've actually taken this sketch right here, and that's what it's supposed to look like when you get the three-dimensional shape off of this. And again, I put that up just for context to emphasize that this comes out, to me, it comes out looking like a croissant. But let's say I didn't have that picture right over there, and I had to produce this myself. I would be rather annoyed because, again, I'm not an artist, but I know we're talking about one arch of the curve, y equals 2 sine of x. So I know that one arch of the curve, 2 sine of x, looks like this. How do I know that? Because I know how the graph of sine looks. And I know that the amplitude here is 2. Not that that's going to do anything for us. I like to just put that down. I know that this is going to go out to pi, again, because I know how the graph of sine works. Now reading in here, each cross-section is cut perpendicular to the x-axis, is a semicircle whose diameter runs from the x-axis to the curve. So here we're really seeing that when we cut perpendicular to the x-axis, we get the diameter right there of our semicircle, and our semicircle is going to come off of the page and look like this. So you can kind of feel that's coming out of the page right there. Look in here, let's draw another one. So again, looking a little bit crappier than the picture that I had up there, but at least I made it myself, right? It doesn't matter how good this is or that we can recognize that it looks similar to a croissant. What does matter is that we can get the cross-section of that figure. And the cross-section is going to be a semicircle. So there's our semicircle. We know that the area of a semicircle is going to be half pi r squared, again, because it's half of a circle. Now here we have to acknowledge what the r is here. Our diameter goes from 0 to the curve, so our diameter is going to be the y-coordinate of any point on that curve. Our radius is half of that. So our radius here is going to be half of y. Half of 2 sine of x is going to give us that the area of this cross-section is 1/2 pi times half of 2 sine is going to be just sine of x squared. Now we know that our volume is going to be the integral of our area times dx. Again, we're talking about our slices going, they're running vertically, so our widths of the depth of each of our slices is going to be that delta x, which translates into the dx. Now we just need to find our limits, and we're talking about one arch, so it's going from 0 to pi, and I see some scary stuff in there. I do know that I could use trig sub in here, but I didn't teach you guys trig sub. So we're gonna go right over to our calculator and alpha, oopsies. I said alpha window 4. We're running from 0 to pi of 1/2 pi sine of x squared dx. There we go. The volume of this croissant is going to be approximately 2.467. Approximately 2, whoa, that is not a 2. 2.467, whatever cubic units we're dealing with. We don't have units given to us, so we don't know what units we're using. So maybe just put in units cubed. I'm not going to take off points if I don't give you the units for you not saying units cubed. I'm not an elementary school teacher. If we have time tomorrow, I have some pictures that can show you some of these three-dimensional objects. I stole them from somebody. He actually made it his project one year, which was pretty cool to see. So that is what we call a day here. Goodbye. See you guys tomorrow.